Okay, so now today we're going to talk about applications for double integration. Okay, so one application is probability. So recall, for 1D, we can think of a probability density function, p of x, as being some function uh, where, sorry, I'll not put equals there. P of x is a probability density. And we're going to think of this as lowercase p. And we want to find, so the probability, that'll be capital P, of x being in some region, so between some value a and some value b, is going to be given by the integral from a to b of p of x dx. Okay, p being the lowercase x. So typically we're thinking p of x, a lot of times a really common one is some sort of bell-shaped curve like a Gaussian, where that's x there. And the probability density gives some idea, it'll give some idea about where x is likely to be found. So for high values of p of x, relates to an area or a region of the x space here where x is most likely to be found. So the question then is, what about 2D? So 2D, we have a problem where we have now x and y. So this is our 2D case. So we have two random quantities. So two random quantities, and oftentimes we want to know something about both x and y together. So we want to find a probability density. We'll call it p of x comma y. We want to know, basically what the probability is the probability. I'll put p that x comma y is in, and we use our epsilon symbol, some region D. So, and of course that is the double integral of lowercase px comma y dA. All right, and so this region D might be some place in the plane, some sort of shape that's important to us, or it's important, some combination of of the quantities x and y that are important for some aspect of the question we want to ask. So what is an application of this? So an application would be a warehouse where we need to for delivery of goods. So the idea is we have sorry, I'm gonna take that away. We have a warehouse with a bunch of shelves in it, and we're looking above at the kind of the floor plan of this warehouse with all these shelves in it. And we also have some central place where packages get boxed. Right? And so when an order comes in from the outside, it gets sent in, and then a person actually has to go into the warehouse, find the item that's being ordered, and bring it back, send it to the boxing area. From the boxing area, it gets put in the box, and it gets a little sticker put on it that tells the address of where it needs to be sent, and then it has to go into a truck. and that gets sent somewhere across the country to be delivered. So we can think of this as happening in two stages. One stage is that the time it takes, well, I'm going to call that X, to pick item. Pick item from the shelf and then deliver to the boxing area. Alright, and then there's another time, and we'll call that Y to box. So this is the time to box and ship. So it's the time to get into the truck from the boxing area here and to put it in a box and then to send it to the truck. So maybe not to ship, but just to put it in the box and comma put on truck. Alright, so both of these are random quantities depending on, for instance, if the item is very close to where the person who's ready to take an order is, they can quickly get to it. But then some items might be really high on a shelf. Maybe they need a forklift or an elevator to get up there. Maybe they need to walk up several flights of stairs. Whatever, that's in the very far corner of a warehouse, it's going to take quite a while for them to get to it and quite a while for them to come back. So we can think of X as being random. And now Y, if we have some boxing, when we get an item, we need to box it, and so that means we need to find a box of the right size. We need to print off a label. We need to get tape. All of that also is random. There's some random processing that it takes before that thing gets in a box and then it gets put on a truck. Okay, and maybe there's several loading bays with many trucks in it. And so someone actually have to walk, and might have to walk very far, or could walk close by to a close loading bay to get on different trucks. So we can think of Y is also random. So we want to characterize what these distributions are. So first of all, we can say assume that X and Y are independent. That means that the time it takes to pick an item off the shelf and the time it takes to box that item and put it in a truck have no relationship on each other. Alright, so what do we want? What are we interested in? What's the goal here? So the goal is, of course, if you're thinking about how to manage this warehouse, is we want to reduce or minimize, or we want to make sure that X and Y are, I should say X plus Y so I'm going to say that X plus Y, make sure X plus Y is not too long of a time. Because we really want to think of it, what we're talking about here is order fulfillment. Order fulfillment time is X plus Y, right? And we're going to call that capital T, all right? And so, you know, and if it takes one person to pick and one person to pack or box, the total time depends on these two different people, these two different jobs, and so basically the shipping rate is going to be 1 over T. So if the rate of incoming orders is much higher than we have people to pick and box, we need to, of course, hire more people to run our warehouse. And we need to know, essentially, this order fulfillment time, and this is, of course, also random. So how do we measure and characterize the randomness of the order fulfillment time? So let's talk about we'll talk about a specific model now. So let's talk about X has a probability density that looks like this. We'll say it's f of x, and it's going to be of the form 1 over 30. We're doing this in minutes. E to the negative x over 30 for x greater than 0, and 0 for x less than 0. Okay, so what does this look like? It looks like this. So x is a time, and it's a decaying exponential going off, and it has a specific decay time constant. So we can think of this as basically, on average, $30 minutes to pick an item off the shelf and to deliver it to the boxes, right? But sometimes it can take much longer. It can take over here, and sometimes if an item is very close to where the boxing area is, it can take a very short amount of time to deliver a package. So it really depends. And maybe an item is misplaced in the warehouse, or maybe there's some confusion about the location of it. It might take a long time before that item is actually discovered, and so you can get some very rare events where the time is much longer than 30 minutes. All right. And so now we'll say y has a similar probability difference density, and we're going to call that g of y, and that's going to be equal to, we're going to say that's going to be 1 over 10 e to the negative y over 10, and that's for y greater than 0, and 0 for y less than or equal to 0. All right, so with these two probability densities, we want to now find out. We'll start about a specific problem. We'll start off with a specific problem. So we have our UPS trucks leave warehouse at 9 p.m. But let's say if we're an online retail organization, maybe we have lots of orders come in after 8 p.m. After everyone has dinner, after the kids get going to bed, then people open up their computers and decide to order whatever item they want to order and have it delivered. And so they know that customers are satisfied when orders are shipped in the same day. So the question is, how many orders after 8 p.m. make it to the truck? All right. And that will be a good metric for how well we can serve our customers if we're managing this warehouse. So let's go review what we need to do. All right, so that means we need that t to be less than, we want to find probability. So I say the goal here is to find, we want to compute t is less than or equal to 60 minutes. So if an order comes in from 8 p.m. onward, we want to know if we can get it in the truck before 9 p.m. So we have 60 minutes. And so to do that, we need to come up with a probability model. So we have f of x, which is the probability for picking an item and giving it to the boxing station, the time it takes. We also have g of y. So now the probability density then is going to be px comma y is actually going to be the product of the two, f of x times g of y. Okay. So then the probability then, so we can rewrite this as probability of x plus y is less than or equal to 60. And we can also assume that this is greater than 0. And that's going to be an integral over some region of the 2D space of p of x comma y dA. Alright, so what is this domain, this region? Well, it's going to be the points x comma y such that x plus y is less than or equal to 60. And I should have done this again. Because times can never be negative, we always make sure that that x plus y has to be positive as well. So what does this look like? What does that look like in the plane? So we can actually write that in the plane. So y then is equal to, this implies that y is equal to 60 minus x. So that's a linear equation. We can draw out what that looks like. So our region is, so at x equals 60, y is equal to 0. So there's 60. And over there, when x is equal to 0, so this is the x-axis here, and here's the y-axis, it's going to be 60 is there as well. We can draw a line going through it, mostly straight line. So the region D is all this region below that line. Okay, so that's the region we want to integrate. So let's operationalize our integral. So if we move this down here. So we're going to integrate over x. So the bounding lines then for the y interval. So if we're going to think about our making hay, right? We're going to integrate like that. So what we want to do is integrate y first, right? So we're going to integrate like that between these lines, and at the end of the day we're going to integrate left and right. So the outer integral will be the x integral, so we'll make that 0 to 60. We'll put a dx there on the outside. And on the inside, we'll put our dy. And it's going to be, what's our function there? And this integral is going to be from 0 all the way to 60 minus x. Okay? That's going to be p of x comma y. Alright, so let's rewrite that again. 0 to 60. And now I'm going to put 0 to 60 minus x. And we're going to put in our functions. Remember what they were? Okay, I can remember what they are. So they were going to be, it was going to be 1 over 30 e to the negative x over 30. Now it's going to be e to the negative y over 10. Now it's going to be divided by 10. dy dx. We're doing the y integral first. So let's go down there. Leave our integral, our outer integral alone. Now we see right off the bat we have a 30 and a 10. That becomes a 1 over 300. Okay, looks good. And then what we have then is we can, because we're doing integral in y, this part right here can be moved out, so we can have an e to the negative x over 30 integral 0 to 60 minus x e to the negative y over 10 dy dx. Okay, so 1 over 300 integral 0 to 60 e to the negative x over 30. So what's the antiderivative of that? We can write it down simply enough. It's going to be 10, be negative e to the negative y over 10 from 0 to 60 minus x. And then we're going to put a dx on the outside of everything. So we see a 10 there and a 300 there, so that brings us down to back down to 30 on the outside. Lots of rewriting. So sorry, that's a 30 there. And then, so we move that 10 out, and then we have to then evaluate this. So we can evaluate it at, that'll be a 1 minus e to the negative 60 minus x all over 10 dx. All right, so we're getting close here. So 1 over 30. All right, and now we're going to distribute in. So we're going to distribute in this to both of those. So we have e to the negative x over 30. We have minus e to the negative 6, because 6 over 10 there. And that becomes then a, so let's do a little math over the side. We have a negative x over 30, and also a positive x over 10. All right, so that becomes a, I'm going to multiply this by 3 and that by 3, so we get 30 and 30 above and below. And that gives us a positive 2x over 30, or rather x over 15. All right, so that gives us a positive x over 15 there, dx. All right, so now we can compute this. So we can take the antiderivative of the first one, and that's going to be negative 30 e to the negative x over 30, evaluated at 0 to 60. And then here we have a negative as well, and put the 1 over 30 there. And then we have, and we can even move this e to the negative 6 out, because it doesn't matter. And we have a 15 e to the x over 15, 0 to 60. Okay. All right. So now all we have to do is the arithmetic part. And we see the 30s cancel, and we get a 1 minus e to the negative 60 over 30, which is going to be negative 2, right? Does that look good? Yes, that looks good. Okay, so and then finally we also have a negative. We have an e to the negative 6 right there, right? A negative 6 over 30. And then we see there's a 15 there over 30. That actually becomes a 2, right? And then finally we have 1 minus, and then 60 over 15 is e to the 4th power. Okay? All right, so let's keep writing this. That's 1 minus e to the negative 2. And then minus, and then we have to distribute this in, so we get an e to the negative 6 over 2. And then we have a plus e to the negative 2 over 2. Okay, so we have a minus there and a oh, sorry, I made a mistake here. We should have had these signs the other way around, like that. So we're going to have a plus there and a minus there. That's better. Okay. So now what we have then, just to simplify it up a little bit, we see we have a minus 3/2 e to the negative 2 and a plus 1/2 e to the negative 6. So that's our result. And turns out if we want to calculate this, it's easy enough to plug this into a computer. We can get 0.7982 or about 0.8 if you want to round up. So the probability for the fulfillment time to be less than 60 minutes is around 0.08. So 80% of orders within 80% of orders, I should say, get shipped in 60 minutes or less. So so there you go. There's your nice result. So that's how we do it. So thanks very much.